Good afternoon, everybody. Thanks for coming, either in person or online. My name is Nuno Moreiro, and I'm happy to present today's speaker, Professor Jim Stone from the Institute for Advanced Studies. I've known Jim for several years now, I think probably since I was a young postdoc. And, I've always been in awe of not just the physics work, but also the numerical work that goes into enabling that physics work. And so the opportunity presented itself this fall to invite Jim to come over and tell us about, today about the more numerical aspects of the astrophysical simulations that he works on, and tomorrow when he visits the physics department about the more astrophysical aspects of things. So Jim, I think, needs no introduction, but is recipient of many awards. The one I'm most envious of is probably the James Craig Watson Medal of the National Academy of Sciences, entirely deserved. And I won't take more time. So Jim, thanks for joining us, and I look forward to your talk.
Well, thank you.
Thank you.
Thanks for the introduction, and thank you for the invitation to come. It's a pleasure to be here. Princeton also has an Institute for Computational Science and Engineering, which I was very involved with when I was on campus. And so it's really interesting to be here to see how MIT is organizing computational science sort of writ large, and how students, postdocs, faculty interact in the center is very interesting to me. So I'm enjoying my day here visiting and talking with people. My research that I'm going to present today is very much about sort of traditional computational science, namely solving PDEs on a computer. I understand there's a lot of interest in AI and its future here. There's not going to be a lot of AI here in this talk, I'm afraid. This is all about, sort of old school numerical analysis and solving PDEs on computers. And I just thought I'd bring you up to date about where we stand on doing that sort of thing in the field of astrophysics. It's a informal seminar. I mean, please interrupt me at any point. It's a small group, and happy to answer questions or have some discussion at any point. But I thought I should start at least by giving you some motivation about why. You're probably not all astrophysicists, so you may not know what kind of problems that motivates what we're trying to do. I'll give you motivation. I'll spend a little bit of time about the numerical methods that we're using. I thought that would be appropriate in this venue. I'll talk about running an Exascale, which is sort of the game changer recently. Give you an example application, and talk a little bit about the future and what might be coming in the next 5 to 10 years. So in astrophysics, I think it's easy to find motivation because we have these amazing telescopes that are providing these amazing images. The latest being James Webb Space Telescope. There's an image of the Carina Nebula. This is, interstellar material. It's plasma in between the stars, out of which new stars are forming. So previous generation space telescope HST has provided motivation, and now JWST is providing these infrared images. It's really just spectacular, the small scale structure and kinematics of these regions that are being revealed by these telescopes. And this is a very small part of, the Milky Way galaxy. We can take images of external galaxies and see how these clouds in the interstellar medium are organized on galactic scale. So the image I just showed you would be, a few pixels in one of these images. So the left image is an optical image from Hubble showing you all the stars in the galaxy, and the far right image is the JWST infrared image, and you can see the clouds and holes in the clouds in the interstellar medium being sculpted by supernova and feedback from stars. And so basically we're trying to understand these systems, how stars form, how galaxies form, how they evolve. All of those problems involves modeling the dynamics of this gas, this plasma dynamics. So if you want to understand formation of stars, planets, galaxies, we need to understand the plasma dynamics directly. So what mathematical model describes that? Well, if we start at the very, very beginning, the mathematical model really is the Maxwell system for evolution of the phase space density of particles, as well as the Maxwell equations for evolving the electromagnetic fields, magnetic electric fields in the plasma. And that's appropriate for collisionless plasmas, where the mean free path of the particle is large compared to the system size. There's great expertise here at MIT on plasma physics, and there's a lot of work being done in basic plasma physics here. But in fact, in many astrophysical systems, the mean free path is not much bigger than the system size. So for example, And that interstellar medium image I just showed you, while the mean free path may be astronomical units in length, much bigger than meters, still the system size is light years in size, many, many AU. And so this mean free path is still small. And so the plasma is basically collisional. It means the distribution functions mostly Maxwellian. You can use the equations of MHD to model these systems. And so I've just written them out as system of conservation laws, conservation of mass, conservation of momentum, energy, along with the induction equation for evolving the magnetic fields. And this is the appropriate mathematical model for following collisionless plasma or collisional plasmas that can be treated as a fluid. And included viscosity and resistivity here, dissipation, because this will be important for some of the applications we're talking about. To close the system, you also need an equation of state. And again, astrophysical plasmas are rather simple. Usually an ideal gas law works very, very well. So just writing the pressure as NKT, where you need some additional parameter, the ratio of specific heats, the gamma for the gas, which depends on whether it's monatomic or diatomic. But those are details. Basically, a simple equation of state works well. There are exceptions, neutron stars and other objects in astrophysics where the equation of state is much more complicated. But generally, the idea is you need an equation of state, and there's many to select from. So that's the mathematical model that we'd like to solve. And the challenge is solving the system of equations. There are hyperbolic conservation laws. There are complicated equations to find analytic solutions for. And one of the complications, as I'm sure many people well know, is that these system of hyperbolic conservation laws admit plane wave solutions. You're used to this in regular fluid dynamics. The complication with MHD is that those wave speeds are anisotropic. There are 3 wave families in MHD, and the wave speeds depend on the direction of the wave vector relative to the magnetic field. Moreover, sometimes these wave families are degenerate. So you may not have 3 independent waves, there may only be 2, which means mathematically speaking, the equations of MHD are not strictly hyperbolic, because sometimes the eigenvalues are degenerate. Sometimes there's only 2 modes instead of 3. And so that makes the mathematics of the MHD somewhat more complicated than hydrodynamics. But as an example, I show you, animation of the propagation of 2 of these wave families. The blue is the density perturbation, small amplitude linear wave. Green is the magnetic field. You can see on the left panel, the density and magnetic field are in phase. There's a fast magnetosonic wave. On the right-hand side, the density and magnetic field are out of phase. That's the slow magnetosonic wave. That's the basic distinction between those 2 modes. When the perturbations are in phase, the restoring force is larger, the wave propagates faster, so that's the fast wave. So being able to capture these waves accurately with your numerical method is very, very important. And so building schemes that capture the wave dynamics properly is important. But in addition, they're not just linear waves. These equations admit discontinuous solutions. Somewhat remarkable, actually. They're PDEs, and yet formally the derivatives are divergent, but nonetheless, you can have discontinuous solutions. Those can be shocks. They can be contact discontinuities. They can be slip surfaces where the velocity components change discontinuously. They can be current sheets where the magnetic field components change discontinuously. All such things exist in these MHD flows, and capturing those accurately is also important. And moreover, the shock dynamics is very complicated. Interactions of shocks with discontinuities is a very challenging problem. The classic problem is how a Mach 10 shock interacts with a spherical cloud. So a problem that's can only be addressed either experimentally or through simulation. So here's an example of how a shock, gets refracted around the blob. It collides on axis, generates this very complex shock-shock interaction and contact discontinuities. Downstream, it excites Rickmeyer-Meshkov instabilities and Rayleigh-Taylor instabilities, which shred the cloud. Cage instabilities occur to produce these mushroom caps. It becomes a complete mess. And capturing this dynamics again accurately and robustly with a numerical method is also a very, very important aspect of using these schemes. So what kind of schemes can we use? I would generally classify these methods that are available based on the discretization strategy. You can either discretize the underlying quantities on a spatial mesh, and that results in, say, finite difference or finite volume or central schemes. Or you could discretize them in spectral space using a spectral decomposition. You can use global basis for that, so Fourier or Chebyshev, for example, and those would be globally spectral methods. Or you can use local polynomials. That gives you discontinuous Galerkin methods, which are becoming very, very popular. Or you can use methods that are based on a Lagrangian discretization. For example, particles that move with the flow, so-called smooth particle hydrodynamics, is used in astrophysics. All of these methods have strengths and weaknesses. You can take courses, semester-long courses on just going through some of these methods. Obviously, I can't cover them all, but I would just say that finite volume methods are what I know and love. They've emerged as accurate and robust methods for shock capturing. That's their greatest strength. They are ideally suited for modern HPC systems. So pretty much everything I'm going to talk about from here on in is all about using finite volume methods for these approaches. Not to say that these other approaches aren't useful, but I would argue right now finite volume methods probably dominate supersonic dynamics for compressible fluids at the moment. So for those who are not familiar, and again, I hope this is not too low level, I thought I would yes, good question.
Would you revise your statement if you were just interested in subsonic turbulence, for example?
Yes, at low enough Mach number, because the problem with the finite volume schemes at the moment, or at least using the compressible form of the equations, is you're limited by the sound crossing time. And if you're truly at low Mach number, then it's a somewhat different ballgame. Now, to be careful, there are finite volume methods which are modified to handle low Mach number flows, and they work extremely well, even for low Mach number. If you were truly incompressible, then I would say that then things like spectral methods, I think, begin to really become appealing.
I think, yeah, I agree. They're just not as competitive in HPC systems, I think, as finite volume.
Yes, I think n log n isn't quite as good as n. And when n is really, really big, it makes a difference.
Absolutely. As
part of it, and part of it's communication. And others, people who are experts on spectral methods here, and they know more. But I think for incompressible, yes, spectral is very important. I think DG is, of course, this great hope. It's still yet, I think, to reach that promise because it's still having trouble with shock capturing, in my impression. But it might actually, at some point, begin to take over. We'll see. We'll see. I mean, you can do fourth order finite volume. So DG only is attractive if you can go more higher than fourth order, because when you just do fourth order finite volume, it's fourth order. It's fourth order. It's fourth order.
Thank you. Yeah, sure.
Okay, so again, maybe if people know all this stuff, I can rush through, but I thought I would just give you a couple of slides, 3 slides on exactly how finite volume methods work, just so you have a sense of what we're doing here. And it all comes down to the initial discretization of the variables. And once you've just made that decision, everything else sort of follows from simple numerical analysis. And in finite volume, that discretization means you take, your unknown solutions U, and you integrate them over the volume of an individual cell. So the I minus a half, I plus a half indexing is to represent the boundaries of the cells. And the delta X, delta Y, delta Z are the volumes or the length scales of the cell. So you integrate each of the conserved variables over the volume of the cell, and you store the volume average cell-centered value. In the center of the cell, you have representation of the volume average quantity. So the mass density, energy density, momentum density averaged over the volume stored in the center of the cell. For the magnetic field, you have to do something different. You have to integrate the magnetic field over the areas of the cell, of the faces of the cell, and you store each component of the magnetic field at the corresponding face. So for example, the X component of the magnetic field is stored on the X faces of the cells, averaged over the area of the face. So those are the way you discretize the hydrodynamical and magnetic field variables separately, and so the magnetic field components are cell faces. And then to update them, you use fluxes for the conserved variables, which are again area averaged on the surfaces of the cell, and they're also time averaged over some time step delta t. You average the flux over that time period, and that's the flux you're going to use to integrate the conserved variables forward. And for the magnetic field, you have electric fields, that, after all, dB/dt is curl of E. So E is like the flux of the magnetic field. And those are at the cell corners, and they are integrated over the lines, over the edges of the cells. You need a separate discretization because the hydro variables are following, divergence of fluxes, and the magnetic field is a curl of electric field. And so there's fundamentally physically different conserved quantities. You're not conserving the volume average magnetic field, you're conserving the area average magnetic flux. And that's represented in just the PDEs themselves. And so you need to have this different discretization, but with that, you preserve mass, momentum, and energy exactly. And you also preserve the V constraint because you conserve magnetic flux exactly. And so with this discretization, you have some very nice properties that emerge directly just from choosing this discretization. And after that, how do you integrate them in time? Well, I guess the idea from Godunov, which sort of, I think is a nice way to explain it, is to say, well, let's try to build in the analytic solution for how these volume average values would evolve. Imagine you just quite literally took the spatial representation of the flow being a bunch of step functions. So you have a piecewise constant volume average value in each grid cell. And you asked, how would this analytic function evolve in time? Each of these discontinuities is a Riemann problem, the interaction of two discontinuous states. And so it would evolve into this solid line at some late time. You'd launch shock waves and rarefactions from each cell. And until the shock waves cross the cell, each Riemann problem is independent. So you would be able to calculate analytically what the shape of this curve is up to a time delta t less than the crossing time of the cell. The CFL condition ends up getting built in this approach. So all I got to do is calculate this complicated shape and then integrate it over the volume, and I'm done. And that seems really, really hard. But in fact, I don't need to know what this complicated shape is, because by conservation, I just need to know what the flux is through the boundary of the cell. All I need to know is the solution to the Riemann problem at the location of the interface. I don't need to know it everywhere. I don't need to know the whole shape. And so all I got to do is solve the Riemann problem. Blow this one up. The Riemann problem in the space-time diagram is shown on the right-hand side there. I just need to know the solution on x equals 0, which means I can use approximate Riemann solvers. I don't need the full shape. I just need to know what the fluxes at x equals 0 is, and that can be calculated exactly using simplifications, approximate solvers. So that's what we do. We calculate the fluxes, then you integrate the volume average values forward using that obvious discretization. So that concludes with all the pieces we need. We need a Riemann solver to calculate the fluxes. In MHD, it's a little complicated because, as I said, the equations are not strictly hyperbolic, and there's these three-wave families, so Riemann solvers get very, very complicated. But we don't need the exact solution. We don't need exact nonlinear solvers. We can use approximate linearized solvers, local Lax, Friedrichs, LLF, HLLE, HLD, Rose linearization. They all work very well for calculating the flux at the interface. Of course, we don't want to use spatially first order piecewise constant values. You can go to higher order by representing the distribution of the fluid within a cell using piecewise polynomials. And there's a whole literature on how you do that to preserve total variation, diminishing TVD, how to have extreme preserving reconstruction methods, and so on. Those are very, very advanced. And one of the advantages of finite volume methods is you can leverage all of that literature to build robust methods for discontinuities. And then finally, you also want to be temporally higher order. You don't want to just be spatially high order. And so you can use method of lines and use strong stability preserving SSP integrators, RK2, 3, 4, up to whatever order you like to achieve whatever spatial order and temporal order you like using these reconstruction and time integration methods. And there you go. Now you have a higher order finite volume method that conserves things like dB and also has excellent shock capturing capabilities through these Riemann solvers. So that's basically how these methods work. How do we know they work? They require these validation problems. So an obvious one is the linear waves. I just showed you the movie of waves computed with one of these numerical methods. And so we can do a little better. We can calculate the L1 error in the wave solution for different numerical resolutions and confirm that the wave error is indeed converging at the rate which we expect. So here, for example, is the convergence of linear wave errors for each of the three wave families for a bunch of different methods from second order to fourth order. And you can see how they're all converging. The second order methods converge nicely. the fourth order methods converge for two of the three wave families, because in fact, these methods are not strictly, what I'm showing you here is not strictly fourth order, because that requires something special in the fast wave for the pressure and for how you convert volume average values to pointwise values at fourth order. So it actually was remarkably that it's fourth order for two of the wave families, but not the other one in 1D. So we, you can confirm that these methods are convergent until you hit basically round off error. Those are linear solutions. I told you about shocks. So you also want to make sure you run discontinuous solutions, so-called shock tubes. This is the result of one particular initial value problem where, again, the initial conditions was just a single interface with two constant states, one in the left, one in the right, everything constant. And you let that interact, that single interface interact. And this particular problem has been construed to give you a discontinuous solution in each of the 7 characteristics in these 3 wave families. So you choose the left and right states carefully such that you end up with the solution being these discontinuities. And again, you can see how the finite volume method has captured them all extremely sharply, no Gibbs ringing at all. What looks like ringing in some of these is actually different discontinuities. You got to catalog them all. There's a fast shock, FS, moving to the left and to the right. There's a slow shock moving to the left and to right. That's 4 of the discontinuities. There's also rotational discontinuities that you cannot see in the density because they're associated with Alfvén waves, and Alfvén waves don't change the density. So in the transverse component of the velocity, you can see these rotational discontinuities. And then finally, there's a contact discontinuity in the middle. So they're all captured extremely sharply and nicely. That's one of the great advantages of these approaches. And this particular problem is not a 1D problem, it's a 3D problem with the shock run at an angle to the mesh, and we're just taking a slice through it. So you can see how even in higher dimensions, these methods still capture these plane waves extremely sharply. And then finally, we can do code-to-code comparisons. And I think an interesting one that I've been involved in is comparing the results for the Kelvin-Helmholtz instability. It's where you have a shear layer, which is unstable at the interface. And this is a resolved shear layer with a smooth initial profile between the 2 background shearing velocities. It also has explicit viscosity and heat conduction. So it's a Wells-Post problem in the sense that there's a resolved reference solution. There's a fixed Reynolds number and Prandtl number here. You have a smooth interface initially, and so you can converge to the result. So the color image shows you each column is a solution computed by a particular code at a particular time. Each panel is a different time, and you can see how the KH rolls up in this cat's eye. It actually becomes unstable to secondary instabilities and gives you this mess at the bottom. And the solution in this rightmost column is computed by Daedalus, a spectral code for which we have the expert here. And that is the resolved reference solution. We know that because if you increase the resolution in the solution, nothing changes. And what's remarkable is that the finite volume solution agrees exactly, pixel for pixel, even in this complicated turbulent regime. And you can do better. You can calculate the L1 error in the solution by just taking the finite volume solution and subtracting off the spectral solution. And again, you can see convergence to the solution with the L1 error being 10 to the minus 5 in the volume, which is, at our level, extremely small. And so you can get exact correspondence between the solutions. You get basically spectral accuracy. You're getting finite volume methods that are giving you spectral accuracy at a very comparable cost. In fact, to be honest, the finite volume is less expensive than the spectral calculation in this particular problem. And so doing these kind of code comparisons is very interesting. I think actually there's more work to be done in comparing, say, high order discontinuous Galerkin spectral methods and finite volume methods at a higher order. I think there's some interesting work still to be done to figure out apples to apples tests and see what are the most appropriate methods for different problems. Okay, so that's my sort of review of the basic underlying methods. And then afterwards, there's lots of more ingredients to add. One of those can be adaptive mesh refinement. It's become a very important tool. Basically, you want to resolve spatial regions, subvolumes at higher spatial resolution. You want to have a mesh which adapts automatically to regions where small features emerge. There's various kinds of AMR that are implemented in various kinds of codes. They're so-called patch-based AMR, where suppose you had some, the ellipse represents some region where you want to increase the resolution, you can cover it with patches of fine meshes. Or you can use block-based, where you break up the background root grid into blocks, and then you can only refine blocks one at a time. So this block lies within the refined region, so you refine this and you refine it again. So you refine blocks upon blocks. Or you can use so-called cell-based, where each individual cell can refine independently. These are three different choices, completely different implementations of AR, and are used in different groups. We've settled on using this block-based AMR because it's so efficient on HPC systems. You can see that it's not the most efficient in use of grid cells. There's more fine cells needed than in, say, the patch-based AMR. So in principle, there's more floating point operations, more work to do. However, the blocks only communicate through boundaries. There's no overlap between the fine and coarse cells. So the solution is only represented by one point, and you don't have to worry about inconsistencies in the pressures or other derived variables between the meshes. Most importantly, when you divide this up with MPI, it's so much easier to load balance the block-based. And so the block-based ends up being more efficient. And so even though it's doing more calculations, it may run faster on an HPC system than the other approaches. And so when you're running an exascale, block-based really seems to be a big advantage. And so we've completely adopted block-based. Not to say the other approaches aren't very, very powerful, but for us, using block-based is really the way to go. And the parallelization is straightforward in these block-based. Since you have all these individual blocks, they're always the same size, same number of grid points. You can easily just use domain decomposition for distributed memory parallelization. You just give each block to a different processor, and you communicate the boundaries for the blocks using MPI. You can use shared memory parallelization within each block. If the block is a 64-cube block of cells, that's a lot of parallel work you can do inside the block. And so you can have hybrid parallelization doing distributed memory on the across blocks and shared memory within each block. To organize the blocks with AMR, so to keep track of them all, then using these binary trees is extremely useful. It's a quad tree in 2D, an oct tree in 3D. I won't get into the details, but this way you can preserve locality. You can make sure that blocks that communicate to their neighbors are located on the same processors or very close to each other. So that reduces the amount of communication that has to occur across the machine. And again, what has to be communicated? You just communicate so-called ghost cells. So if the white cells are the active cells being updated on a block, then you have these ghost cells, which are located on your neighboring blocks. And those you get by MPI communications to your neighbors, with up to 56 neighbors per block with AMR. So each block may need to send up to 56 MPI messages. Seems like a lot, but actually that's not, it's only with AMR and only in special sort of situations with AMR, so it doesn't always happen. But yeah, up to 56 neighbors.
And typically, what criterion do you use to decide whether to refine the grid or not?
Excellent question. And that becomes more an art sometimes than a science. But of course, you can use any criteria you like. You can use the functions themselves, so that if the density or energy or magnetic field were to exceed some value, you would refine. You could use any derivative that you like, whether the first or second derivative of those variables exceeds some limit, then you would refine. The original Berger and Oliger papers suggested that you compute the truncation error. That is to say, you always run with a fine solution and a coarse solution. You compare the difference between these two, estimate what the truncation error is, and if that's bigger than some criteria, then refine. You can do that as well. The problem with doing that is that every shock always has first order truncation error and is large, so you have to limit it at some point. But basically, every application would use a different criteria for doing AMR. And in fact, that leads me to this. Maybe this is what you're really asking me about, is that, does it matter? I mean, should an AMR mesh just give you exactly the same solution as what you get on a regular uniform mesh? And so it really is just optimal to use AMR. There's a standard test problem for Astrophysics code against a KH instability. So it's, two flows, shearing past each other. the interface has gone cat's eye unstable and rolled up, but it's also unstable to secondary mode. So it's generated this very complicated mess that you see in the middle. And when you blow up that little square, you can see the small scale detail. You can see the AMR grid on the bottom. When we ran this test, we were confused by why our solution wasn't exactly the same, pixel to pixel, like we saw before with previous solutions given in the literature. And with modern machines, we said, well, let's just do this at the full resolution of the finest mesh on a uniform grid. It's not that expensive. We'll just do the whole darn thing on a uniform mesh. And that's the solution you get when you run this initial value problem on a uniform mesh. The cat's eye doesn't go unstable at all. It stays this nice, stable cat's eye, right? What happened is that this interface is subject to parasitic modes, but unless there's a perturbation, those modes won't grow. And on a uniform mesh, the truncation error is uniform and there's no perturbations. So only when you have AMR, the truncation error changes discontinuously when you go from one mesh to another. That seeds small perturbations in the truncation error, seeds the physical instability, and you get a mess. And so yeah, the solutions are not going to be the same. They're only ever going to be the same when the truncation error just doesn't matter, when the solution is completely resolved. But if the solution has any influence from the truncation error, they're not going to be the same on an AMR mesh compared to uniform mesh. And you have to decide whether that's important or not, or whether you have to worry about that or not. I mean, if you really want to resolve solution, you have to use dissipation corresponding to the coarsest grid, which is not something you want to do generally. And so, you know, resolved solutions with AMR often is not an option. Otherwise, you have to use the full mesh everywhere. So it's an important point to know about. It's not a showstopper. You just have to know about it. After all, any real KH interface is going to be perturbed by all kinds of junk. Those images I showed you at the beginning, there's never such a thing as a perfectly undisturbed interface in astrophysics. So this is probably the right answer anyways, with lots of perturbations in. Okay, so we also want to add more physics, not just more tools like AMR. Another piece of physics that we're using is particles. It's very useful to evolve particles along with a fluid, just following their equation of motion. This is work done by George Wong and Philip Kempsky at Princeton. We've added both Lagrangian tracer particles, where the velocity of the particle is just the local velocity of the fluid. So the particles just move with the fluid. The KH instability test, again, showing you the comparison between a passive contaminant and Lagrangian tracer particles, showing you the two different fluids. I can also add charged particles that move along the magnetic field lines, spiraling along magnetic field lines and scattering off magnetic field inhomogeneities to study how, for example, cosmic rays are accelerated in MHD turbulence. And the code's being used, and then we're involved in a big project to do this using a particle integrator to follow charged particles. You can put the feedback with the particles back in the fluid and study a whole range of problems related to streaming instabilities. And that's another whole class of things that work is underway on. It turns out that this is not fluid dynamics, but it turns out that there's other systems of equations where these AMR meshes and these grid-based methods are very appropriate. Another one is for solving the Einstein field equations and numerical relativity. Turns out the AMR, block-based AMR, is an ideal approach for solving finite difference methods. So you can implement high-order 6th to 8th order methods, finite difference methods, for solving the equations using the so-called Z4C formulation. Einstein field equations are both a coupled system of hyperbolic equations as well as elliptical constraint equations. So Z4C is a particular way of damping that system of equations, the constraint equations, properly. So this is all being implemented in the code I'll talk about, and can do black hole mergers now on these adaptive mesh refinement using the same infrastructure. And the right-hand panel shows the emergent gravitational waves, showing the in-spiral, the merger, and then the ring down of the remnant, calculated using these methods. Also showing convergence of the resulting solution using fourth order convergence using fourth order methods. So this is a very useful capability because many problems in astrophysics involve relativistic dynamics. So, for example, there's many problems involving merger of compact objects in which the gravitational waveform and emission is very, very important, but along with the fluid dynamics. But you can write down the relativistic fluid dynamics in the same conservative form as I showed you before, conservation of baryon number, stress energy tensor, and magnetic field dual. And you can then use the same technology, the same framework, building Riemann solvers for general relativistic MHD, the same infrastructure with spatial interpolation, time integration to build higher order finite volumes for GRMHD in full dynamical spacetime, combined with the numerical relativity solver I showed you before. And so here's an animation of a merging neutron star, which is emitting gravitational waves and spiraling inwards. Eventually, the neutron stars begin to crash into each other, generate shock waves. At their interface, they begin to eject material through tidal forces. You see these spiral shock waves that get generated in the merger process. Those carry off angular momentum and eventually start spinning down the merger remnant. And so it sort of becomes quasi-spherical as this high mass remnant now, this rapidly spinning high mass remnant loses a little bit more angular momentum. And suddenly at some point, boom, a black hole forms in the middle. With full numerical relativity, you capture the formation of the horizon, and you can then study the resulting dynamics of the black holes that you can form in this. So there's a big project. The panel on the right-hand side shows the gravitational waveform emitted from the calculation, and big project now doing these neutron star mergers using these finite volume approaches. And then finally, another very important piece of physics that's necessary in many parts of astrophysics, especially high energy astrophysics, is radiation transport. Because in many circumstances, the photons carry a significant amount of the energy and momentum of the fluid. In fact, in many cases, they're the dominant form of energy density in the problem, much, much more important than the fluid itself. And so you really need to model the transfer of the photons directly. I mean, solving the rate of transfer equation for the photons. Fortunately, in recent work, it's been shown that you can write down the covariant transfer equation in full general relativity in the same hyperbolic conservation form as the rest of the equations, as the fluid equations evolve. So the actual details of the equation don't matter, but just to say there's a conserved quantity related to the specific intensity of the radiation field along a particular direction. And that this conserved quantity evolves through spatial divergence of a spatial flux, divergence of angular fluxes, because photons follow geodesics, they follow curved paths in space-time. So there's angular fluxes here. And there's also a frequency flux, because in general relativity, there's redshifting, so photons can move from one frequency bin to another as they move through space and time. But that's all written out in this conservative form of ddt of conserved quantity plus divergence of a flux equals source term on the right-hand side, emission and absorption on the right-hand side. And so we've built same kind of finite volume methods using Riemann solvers for this equation, and higher order spatial and temporal interpolation for this equation to be able to integrate it just in the same discretization as we're using for the fluid, and able now to do full radiation GRMHD. The one complication is you have to discretize an angle on the sphere. Each spatial grid cell has to contain a little mesh of different specific intensities at different angles, and we're using this geodesic mesh to cover the sphere more uniformly than just latitude and longitudinal mesh. And so it's working very, very effectively for us to use these geodesic spheres. But now we're able to do full radiation dynamics using the transport equation directly. And the trick is that's getting expensive. I mean, by now you're doing relativity and you're doing radiation transport. It sounds pretty impossible, right? But the thing is, computers are getting really, really, really big. Exascale is here. That means 10 to the 18 floating point operations per second. And even for an astronomer, 10 to the 18 is a big number. So that's a lot of floating point operations on these machines. There's a machine at Oak Ridge Frontier, which has been running for almost 2 years. The next machine, Aurora, is starting at February 1st of next year. Both of these machines are providing literally billions of core hours effective time for application teams to run open science problems on these machines. They're billions of times faster than the machine I ran on as a graduate student. I hate to be one of those people. When I was a kid, but it's true. Billions of times faster is really remarkable. The challenge, of course, if you're familiar with using these kind of machines, is they're all based on accelerator architectures like GPUs. And programming these GPUs is complicated mostly because each vendor has their own preferred programming model, whether it be CUDA for NVIDIA or Sickle for Intel. And if you write your code in one programming model, it's not going to run on the other machines. And for me, that's a showstopper because I don't have the time and resources to write a different code for each different machine. But fortunately, computational scientists know all about this, and they've come up with some very smart solutions. The solution that I'm particularly in favor of at the moment is a library called Kokkos, a project at Sandia National Lab. It's simply a set of C++ templates and abstractions. It's just a C++ library that basically translates your C++ into whatever programming model you want. When you build your code, Kokkos will automatically turn the instructions into CUDA, if that's what your target architecture is, or it'll turn it into HIP, if AMD is your target, or if you're just going to run it on your laptop, it just turns it back into C++, and you just have direct general C++, and then you can compile it on using the vendor's compilers on whatever machine you like. And so it makes the code so-called performance portable. It'll run on any machine you like for which Kokkos supports. And they support basically everything, including ARM processors like your iPhone. You can run your code on your iPhone if you want, if it's written in Kokkos. So I think it enables Exascale for people like me who are not going to be able to write codes for every different kind of machine. And so we've written our GR MHD code Athena to a new version called Athena K. It's a sort of a complete rewrite from scratch using Kokkos. It has this full AMR framework using this block-based AMR that I described. It has various physics solvers for Newtonian, special relativistic GR hydro, dynamical spacetimes like I showed you using Z4C, GRMHD and dynamical spacetime, this relativistic radiation transport, all built in. And I don't expect you to look at all the numbers. The point is that it runs on everything. It runs on NVIDIA's, it runs on AMD's, it runs on Intel. Intel number's not there because it was non-disclosure, but I think now it's going to be able to add the Intel numbers to this. It runs great on the PVCs. And so it just runs on everything, and it runs quite well, comparable to code written in the native language itself. So if you compare the performance of Athena K on an NVIDIA GPU with a special purpose MHD code written in CUDA, the performance is about the same. So it's really very comparable. So it's very, very attractive. We're up to 1 billion zone cycles per second on a single device now on the latest Grace Hopper chips from NVIDIA, which is really, really, again, remarkable. The performance in a single device, 1 billion updates. You can do 1,000 cube mesh with an update every second, every wall clock second. It's really remarkable.
Sorry to interrupt again.
Yes.
So MHD isn't just twice as expensive?
Depending on the device, no, sometimes it's more than twice because you almost double the number of variables. And then in addition, things like the Riemann solver are much, much more complicated.
Right. This is like on the further right, because it's about a factor of 2, it's telling me that on that specific architecture, the Riemann solver is
cheaper. I mean, there's
compared to
the one dirty secret about performance portability is that you have to make decisions about how you organize things. And some of those decisions work better on CPUs than on GPUs. And so it's not truly possible to have the best performing code on every architecture and for it still to be performance portable. Unless you have endless if blocks, if CPU do this, if GPU do that. But then if you do that, what's the point? You have 2 codes anyway. So you have to sort of compromise. We've targeted the highest performance on GPUs. So our CPU performance you see is more than 3. Maybe that's the explanation.
How does that compare to the pre-Kokkos versions on CPUs?
Not quite as good. And the reason why is because Athena++ had all this hand-coded vectorization instructions. And while Kokkos provides vectorization by inserting in SIMD pragmas, it's not as aggressive of what Athena++ was doing. And so on certain kinds, so on the, you can't run Athena++ in the M1 Pro because it's an ARM processor. And so you can only run it in x86 mode, which is not nearly as fast. So on the M1, Athena K blows away Athena++. But on the Intel processors where you can use AVX vectorization, Athena++ is a little bit better. Now, you could work hard to do that, but it's pretty good. It's like 20% slower than Athena++, so it's not a big deal. A big issue is, is parallelization and scaling. because you got to be able to run on these large machines at scale. And again, these finite volume methods parallelize great on these machines. So here is a weak scaling plot on an Intel GPU cluster on the left and an AMD GPU cluster on the right. Maybe the interesting curve is the two bottom ones. You know, the performance per GPU is pretty much flat over several thousand GPUs, and the efficiency is about 97% out to 4,000 GPUs. You know, clearly some hardware issues where you get a big drop when you go from, you know, 16 to 32 nodes or something on the AMD machine. That's not our fault, that's their fault. And we've now run up to 64,000 GPUs on Frontier and gotten better than 80% scaling on the whole machine. And so you really are able to exploit the full 10 to the 18 flops on a single problem using this domain decomposition finite volume approach. So that's again what makes this so interesting. If I may, I think can I get on the soapbox and say something? You know, since I'm here at CCSE, you know, there's some thoughts about developing these codes nowadays that might make, namely things like everything's getting more complicated, especially the hardware. And often students don't have a strong grounding in numerical analysis or in software engineering. How could they? Those are complicated topics in themselves. And if you haven't taken courses in those, you wouldn't know it. So I think things like CCSE are really important. Things like the Institute of Princeton was really important to be able to teach classes that would enable students to learn the tools that you really need. You know, there's really important tools that are central to doing software development that I think everyone should be learning. But probably the era of a single grad student running a cutting edge code from scratch is probably coming to an end. It's getting harder and harder and harder. And so we have to think more about how to do, you know, collaborative development projects, I think, in the future. And moreover, some other more personal thoughts. I personally think, for example, my advice is always to stick to established methods. You know, being on the bleeding edge is not always the best thing because then those won't work on certain devices. They won't support your particular choices for programming model, for example. Always stick to the standards. Try to avoid external libraries as much as possible, and keep things simple. The code, in my experience, gets to be really complicated once it's above a few 100,000 lines, really hard to support. And so if you're reaching that limit, you know, try to think about how to keep it simple, or maybe break it up into different pieces or something. I don't know, but I think codes beyond a few 100,000 lines become really hard to manage. Not to say that, you know, again, that's not a hard, fast limit. I'm just saying, in my experience, it gets really, really hard. So let me show you a quick application to these black hole accretion flows, which is a problem of great interest and importance, and something we've been working on for a while. So the left-hand image is sort of an artist's impression of plasma accreting into a black hole. It turns out there's physical instabilities in magnetized plasma rotating around black holes at Keplerian rotation profiles. They're literally unstable to this MHD instability called the magnetorotational instability. And you can see in the simulation of the development of the MRI on the right-hand side, this movie shows you the current density resulting from the growth and nonlinear saturation, eventually saturate to turbulence from some nice smooth initial condition of just uniform magnetic fields. And so understanding how this instability transports angular momentum and drives accretion is a fundamental problem in astrophysics. This is the typical scale of problem done before Exascale, about 512 cubed in 3D. You know, 512 grid points per thermal scale height was about as much as you could afford for modeling this disk. And the image in my start was what we can do now at Exascale. Now we're doing the same problem. This is the same variable, current density, but now it's run at 8,000 squared in 2D, 8,000 cubed in 3D now on the full Exascale machine. And you can see the much greater dynamic range and scales that suddenly emerge when you reach turbulence at this scale. This is a resolved calculation with explicit resistivity and viscosity. It has a Reynolds number of about 1 million. So we're well into the plasmoid dominated forming regime of these current sheets. You know, in fact, this screen doesn't have 8,000 squared pixels, so I have to blow it up so you can actually see the pixel by pixel scale of things that are emerging in here. So you see these enormously long current sheets that sometimes go plasma unstable. They don't always. Not every current sheet here is reconnecting. There's only a few locations where they are. So this is what we can do now at Exascale and try to understand exactly what's going on in this MHD turbulence and how it produces angular momentum transport and accretion. We can go beyond these local simulations and do full GRMHD global calculations. We're not just doing a little patch of the disk, we're doing the entire disk over many decades in radius. This is a calculation that began from a torus, a donut of plasma, which has gone MRI unstable and started accreting. And you can see on the poloidal and toroidal and equatorial slice of the density in this flow. And you can see the turbulence, spiral modes generated. This is so-called mad accretion state for those who are experts. So this is where sort of the state-of-the-art modeling is now in the full global dynamical GR of these calculations. And what does this look like in 3D? Here's a rendering of the data in full 3D. You can see this beautiful accretion flow generated in the density field, these spiral or helical magnetic fields coming off the black hole horizon, which are generating a relativistic jet from the Blandford-Zadiak effect, all captured using first principle calculations here on a finite volume mesh. And these calculations are now being used, or calculations like them by other groups, to try to compare directly to observations like the EHT, which has resolved the plasma accretion near the horizon of the black hole at the galactic center, Sagittarius A star. And so now people are running thousands of models of black hole accretion disks with different parameters, different black hole spins, different orientations, different magnetic field geometries. And then they take images. These are relativistic ray traced images where you emit the photons and propagate them back to the camera to show what exactly the relativistic ray tracing effects would do. And you can then minimize over this full parameter set and find which is the best fit image to the EHT data and hopefully extract what the parameters of the accretion flow are from that calculation. And so this is the kind of thing that these finite volume methods are being used for a lot. I am not involved in this work. This is all work done in Charles Gammey's group at Illinois. I'm just showing you some of the results from this. But they can be used for many problems. We're doing high resolution studies of MHD turbulence in the interstellar medium, propagation of supernova shocks. That paper just came out today, actually, in a multi-phase medium. And also these radiation GRMHD models, which I showed you a non-radiating accretion disk simulation. We're doing them with full radiation transport. And the image on the bottom here shows you the flow structure and relativistic jet produced in a radiation-dominated accretion disk using these methods. So in the last 1 minute, maybe, I'll just say quickly some challenges. One big challenge is scale still. Some of these problems have enormous ranges of scales. From the black hole accretion problem, for example, if you really want to go from the horizon all the way beyond the Bondi radius to the interstellar medium of the galaxy, that's 10 to the 8 in range and scale, 8 orders of magnitude in scale. And if you just use AMR and zoom in to the smallest scales, your time step will be so small, you'll never evolve the dynamics on the outer edges. So how do you handle that? So recently there's an idea that's come up using so-called zoom or multi-scale approaches where it's like a multi-grid method. You just integrate the mesh on the largest scales first for a while till it settles down. And then you move the inner boundary in and integrate this intermediate scale for a while. And you keep zooming in until you get all the way to the horizon. So then you're calculating the flow from the outer region to the inner region. But the time step here is so small, it only evolves for a short period of time. So then you start zooming back out again. When you zoom out, you freeze the solution at the inner flow. If there's a jet, you freeze the jet. If there's a rotating flow, you freeze the rotating flow. And you use that frozen flow as the boundary condition for the larger meshes. You zoom back out and you evolve that for a while. Then you zoom back in and you do this hundreds of times, in and out, in and out, in and out. And you see if it'll settle down to a steady state. And it works remarkably well, actually. It allows us to evolve these torus simulations for tens to hundreds of times longer than we were previously able to. And the flow structure is remarkably similar. One of those images comes from evolving the flow using the zoom in, zoom out technique, where when we zoom out, we don't actually resolve the horizon anymore. We're just integrating a large scale structure of torus. The other one's where you zoomed in and they're both the same. Truth is the one that we're evolving the same mesh all the time. And the zoom is And it turns out when you look at more quantitatively, the solutions really are very, very similar. And so this looks like a very promising approach for handling these large range of scales. And I had to mention AI at least once. And so the way AI is maybe entering this is in trying to learn subgrid models for turbulence. Again, there's experts here on this, and I won't say more, but there's been a lot of work and a lot of interest in trying to develop subgrid models that allow you to run simulations at lower resolution, and then using AI, convert that to higher resolution. I also think AI is really, really important for doing microphysics, like opacity tables, equations of state, subgrid models for star formation and feedback and cosmology. AI may make a huge difference there. Just like in climate modeling, where you can use it for clouds and other microphysics you can't resolve, you can do this in astrophysics too. And so I think AI's future is I don't think we're going to be able to just do, GRMHD rad hydro using AI, because we don't have any training set for it. But I think there's many things we might be able to use AI for, and it'll be interesting to explore that. So with that, I'll summarize just by saying these methods are essential, and it's remarkable what we can do on these big machines now. And it's sort of very, very exciting about the kind of problems we can tackle fully ab initio, I think, in the future. I'll quit with that.
Thank you. Okay, thank you, Jim. It's wonderful. Let's see, are there any questions in the room? Or online, I guess?
So you said that this block decomposition for the AMR helps a lot with the efficiency on GPUs. Does that limit you in terms of other geometries? Like, can you do curvilinear domains and stuff like that?
Yeah, I actually think it's good, not just on GPUs, but anytime you have a large number of MPI ranks, whenever you're going to use highly parallel calculations, then I think that this block-based is easy, because the only communication is at boundaries, just like on a regular uniform mesh. And so that simplifies the MPI enormously. It can work with logically, with curvilinear mesh, as long as your mesh underlying is logically rectangular, then this block-based also works just fine. Now, to be perfectly honest, at Exascale, we have not been using curvilinear coordinates at all, because when you go to very, very high resolution and large dynamic range, I think Cartesian grids are really what you want to use. So for all the calculations that I showed you here, we're all on Cartesian meshes. Even the MRI calculations and the disks, those are all Cartesian grids.
And the nested tori also at the end?
Yes, okay. All of that's Cartesian meshes. Yep. Because at some level, the only difference between Cartesian and curvilinear is truncation error. And if the two are different, then you should be worried that your truncation error is dominating your solution, it's changing the nature of the flow. So at some level, Cartesian should be as good as long as you're resolving the flow. And moreover, in Cartesian, you can use all these fourth order methods because the grid spacing uniform. Fourth order in curvilinear is actually really, really hard, especially if you don't have uniform grid spacing. So I just think there's so many advantages with Cartesian. Not everyone would agree that, but I personally, for the applications, we're doing Cartesian. So Athena K doesn't admit anything but Cartesian meshes. The only thing you can use on Athena K is Cartesian meshes. Whether we could do the star problem on a Cartesian, that's going to be interesting. I don't know. It might be problematic. We could talk about it later.
I mean, yeah, maybe axisymmetric image or 2D.
Yes, you're absolutely right. Axisymmetric is not possible. But then if you want to do axisymmetric, you might not need exascale, and you can just use Athena plus. There's plenty of codes that do 2D curvilinear. So I didn't feel the need to write it for Athena K where, yeah.
On the AMR, oh, sorry, please go ahead.
Thank you. Yeah. I'm well outside of the field, so I really appreciate you making this very approachable. I'm a chemist by training. So
Good. I'm glad it's approachable. Great.
I appreciate it. I wanted to ask sort of the hot topic for HPC in the AI space is low precision or mixed precision. I'm curious if you are seeing that work its way into this field, or just your perspective.
Yeah, it's a great question. Most people doing CFD like myself run at double precision all the time. I actually personally think that's probably wasteful because the truncation error in the solution is probably larger than the round off error, you just don't know. You know, it's hard to measure the truncation error. So you think you're doing better, but you're probably not really doing any better. So to be perfectly honest, single precision is probably extremely useful in many circumstances. Now, when you're at exascale and you're running 10,000 cubed, then I do worry about single precision, because there I feel like you're so far down in the convergence curve, you know, now your truncation error is pretty small. And so it's not for every problem or all aspects of the algorithm, but I'll bet there's significant parts of it where single precision would help a lot. And so, and that doubles the performance on most devices, just going to single precision. Going to half precision, I think gets me a little worried, because, you know, you saw from the linear wave convergence, the error, even with only, you know, 16 or 32 grid points, was already getting to be pretty small, reaching what you would get with single, you know, half precision. And so I think I would be a little uncomfortable going to half precision, but I would be perfectly happy with single for much of it. And it also, again, depends much on exactly what algorithm you're doing. Parts of it, if you've got some iterative solution somewhere, then you can maybe do low precision for that. So I think it's something that, to be perfectly honest, we've been kind of sloppy about, and we're probably wasting a lot of computer time running everything at double precision. That's our dirty secret, and we should probably be a little smarter about that. Appreciate it.
Yeah, thank you for the talk. I was wondering if you had any thoughts on the possibility of extending these models or these methods to regimes that maybe the fluid approximation breaks down, and maybe you need to include kinetic physics, or maybe you include more moments.
Yes, we certainly thought about it. I mean, these methods are kind of related to what people are doing in plasma dynamics. So in particular, with the particle module now and the feedback, you can do so-called MHD pick, where you're looking at the effect of cosmic rays and how they feed back on an underlying fluid model where, you know, so this is streaming instability in that case, where Alfvén waves in the thermal plasma launched by the cosmic rays can then affect how the cosmic rays propagate. So you could use these methods for studying those kind of problems. You know, going to the fully kinetic regime where there's no thermal plasma at all. I mean, I think probably special design pick codes are probably more appropriate. I mean, we haven't really, I mean, there's many such pick codes. Many of them work at Exascale. So, you know, I'm not sure that these methods would be ideal for that sort of approach. I mean, there actually is a new pick code entity, which is adopted many of the basic AMR structure from Athena and is written in Kokkos. And so I think at the end of the day, entity will be very, you know, its core will be kind of similar to what you could do with this anyway. So there is such a thing emerging already. Thank you.
Hey, thanks for the talk.
Yep.
It was really interesting. I'm interested in your general opinion about, clearly, you know, nowadays we can resolve more and more turbulence. The simulations are getting bigger and bigger. We were to sort of decouple advancements in hardware versus advancements in algorithms. How much progress, like relative progress, are you making between the fields? Like, is most of the size and scale of simulations that we're running now just because of advances in hardware?
Again, excellent question. At a point I like to drive home, and every time I teach numerical analysis and quantum computing, most of the advance comes from the algorithms, you know, not from the computing advance. You know, you take Moore's law from the 1980s and you stick a God knows first order method on the computer and you ask what you could do with Exascale. It's nowhere near what you can do with what you can do with these higher order methods. So, you know, things like FFTs, for example, going from n cubed to n log n, I mean, there's no amount of Moore's law that's ever going to fix that. And similarly, you know, going from second order to fourth order can be a big win sometimes. The challenge is that, you know, there's still work to be done with these higher order methods for shock capturing and other things. And so, you know, sometimes you have to be second order in some parts of the flow and sometimes not. But I do think that it's the development of algorithms that outpaces the hardware, but not to negate a factor of 10 to the 9, you know, a factor of 10 to the 9. I mean, it's a bit of both. You know, we could never do what we're doing now on the Cray XMP, you know, that was available in the late 1980s. But on the other hand, if we just had the codes available then, we wouldn't be able to do what we can do now either. So it's a bit of both.
Yeah, it's hard to decouple.
It's hard to decouple, but I still think that it's smart ideas and smart codes are always going to win over just brute force bigger computers.
Thank you.
I'll allow myself one last question, then we'll conclude. I had technical questions, but I'll skip those and just go back to the slide where you said, let me get on my soapbox.
Oh, yes.
So, the statement that we're past the stage where a graduate student can write a state-of-the-art code,
Yes.
I think that's been true for like at least 10 years, right? It just doesn't happen anymore. But so I guess I want to know what you think about this. There was a stage where the same person knew all the physics that there was to know about the problem and wrote that code to solve the physics problem that they had very deep insight into. And that led to sort of, I think, the sort of breakthroughs, well, your work, for example, that I think does just do not happen if you're now at the stage where writing a state-of-the-art code is so complex, right? That it's actually humanly impossible for the same person to be an expert both in the physics, well, the physics has gotten harder as well because we solve the simple problems, right? So I think this sort of conditions the kind of science and breakthroughs that we do. It moves it in a different direction. I was just wondering what you think about
Yeah,
this.
I mean, I think this is a really interesting question and discussion, actually. I think science does have to change. I would say that to make the breakthroughs, I would say the student and the person has to know the physics, though. So nowadays, maybe one can imagine that you don't build everything from scratch. You build a new piece that sits on top of what's been done before that enables you to do a new problem that no one's done before. And that's still, I think, breakthrough, and that's still an important progress. But if you work that way, you still have to know that other piece. You don't have to write it. You don't have to develop from scratch, but you better understand it and you better know the physics behind it. Because if you don't, you'll never really understand what happens when you add this piece on top of it. I think the piece that's lacking is that students sometimes don't learn that lower piece. They just add something on top and something complicated happens, and it's then very hard to figure out what's going on in this full system. So I think it means things like CCSE and PIXE at Princeton have a job to make sure that you teach and train students on the stuff that you can rely on and which works, and this is the way you do that, and this is the physics of that. And then on top of this, now you go off and do your thing. You add the things and study the things that we don't know about that you're going to add on top of that. I mean, it is more work perhaps because you've got this other ground. The foundation is moved, if you like. The foundational stuff that you have to learn is become more complicated. But I think that's, in my philosophical view, the way that things have to proceed from here on in.
Let's thank Jim again. Thank you, Jim.